Hi folks, Mr. Ackman here. Thanks for watching. The topic of today's video is elastic and inelastic collisions. We're going to start looking at collisions in a little bit more detail, this time not only from the point of view of momentum, but also from the point of view of kinetic energy. So what I'd like you to do before I start is pause the video and have a look down here at where we are in the homework schedule, the unit schedule, as well as what the learning goals and success criteria are, and some of the questions that we're going to address in today's video. Please do that now. Okay, thanks, and you're back, and here we go. We're going to start off right away with the concept of elastic and inelastic collisions. Really, this is an idea that relates to kinetic energy. If you can keep track of what objects have what kinetic energy, you will be able to answer the question, is a collision elastic or is it inelastic? Let's have a look at a question that's in the textbook. The textbook is Physics 12 by Nelson, and this is in section 5.2. It's sample problem number 2. You've hopefully already looked at this because it was in the previous lesson, but during a football game you see there are two players coming toward one another with given velocities. They have given masses. It says that when the tackle occurs, they end up running together. So, well, they don't actually say they end up running together. However, you have to know just from, I guess, what they call common sense, that during a tackle, the objects join, or the players join together. So the textbook goes and solves this one. I'm not going to solve it for you. The solution is actually pretty straightforward. All you got to do is find the momentum of player number 1 and the momentum of player number 2, and then the combined momentum P prime of the two. And if you make those equal, you can solve this one pretty easily. They give you enough information about the initial momentum, mass and velocity, and they give you the final mass. Of course, you just do m total equals m1 plus m2. And so all they want to know is v prime. What I'd like to do is skip to the bottom and look at their answer. This is all cut and paste out of the textbook. And you see that it says the final velocity of the players is 2.1 meters per second in the direction of the initial velocity of the fullback, and that's this guy over here, the guy who's running with the ball. All right, so assuming you know how to solve this, and if you don't, once again, go back to the previous section and do that. Assuming you know how to solve this, let's do this. Let's follow the kinetic energy in the question. And what do I mean by follow the kinetic energy? Here's what I mean. Before the collision, each player had a certain amount of kinetic energy. There was player number 1, the fullback. He had kinetic energy, we'll call it EK1. And the defensive player, the defensive back, had a certain amount of kinetic energy. We're going to call that EK2. Now, if we add those up, after calculating them, we're going to get a number. So let's figure out what that would be. Kinetic energy, as you know, is a half mv squared. So we do this. We're going to put in each of the masses, which is going to be 108, and we're going to put in the speed here, 9.1. I'm leaving out units because I want to go a little bit quicker here. You should, however, always include units. A half, here we have 91, and now here's a question. Do I put in the negative 6.3, or do I just put in 6.3? First of all, kinetic energy has speed in it. So this equation does not care about the direction that you're going, so you don't need the negative. But even if you do put it in, keep in mind you're squaring, so it's going to become positive anyway. So I'm going to leave it out, but if you happen to put it in during a test or something, that's not a big deal. Anyway, you got to calculate this number here, and I'm just going to briefly pause my end of the recording here so I can do that. Okay, so I've done a calculation here. I have done a half mv squared for the first guy, half mv squared for the second guy. These are the individual energies that I got, the kinetic energies, and I've added them up to get close to 6,300 joules of energy. Now, what we're going to do is compare that with the amount of kinetic energy after the collision, and we're going to borrow the textbook's answer of 2.1 meters per second. So what is the kinetic energy? I suppose you might call this EK total, which of course is going to be 1/2 m total v squared. And this has to be, which v? Well, it's going to be a v prime. Sorry about my messy writing there. My computer's actually freezing on me as I'm writing, and it's very difficult to see what I'm writing. But anyway, a half m total v prime squared. So that'll be 1/2 of the combined mass. So we have 108 plus 91, that's 199 kilos. And we have to multiply that by the speed squared, which is 2.1 squared. Now, what do we get there? I'm going to pause the video one more time and do a calculation. Okay, I've done the calculation now, and as you can see, the kinetic energy is only 439 joules. So what do you notice has happened here? Before the collision, the total amount of kinetic energy by all the players involved was over 6,000 joules. But when they tackled, when they joined up and ended up moving slower and getting heavier, they lost a lot of kinetic energy. The kinetic energy declined to under 10% of what it was in the beginning. This is what we call an inelastic collision. EK, in the end, EK prime total, is not equal to what it was total between all the players in the beginning, no prime. All right? Can you guess, therefore, what an elastic collision is? I'm sure you can probably guess what it means. It means that EK total in the beginning is equal to EK total prime in the end. Now, keep in mind, this is not the law of conservation of energy. No, no, no. This is the law, or not a law actually, just an idea about conservation of kinetic energy. So please don't mix this up. We're not saying that sometimes the law of conservation of energy applies and sometimes it doesn't. Remember this, it's extremely important, which is why I'm really emphasizing it now. This is just an idea about kinetic energy, which is why at the beginning I said, follow the kinetic energy. Now you might be wondering, still you have this feeling that energy is conserved, and you're right, total energy is conserved in any interaction. So if we lost all this kinetic energy that we can see by comparing these two numbers down here, where did some of that kinetic energy go? I'm going to ask you to pause the video now for a moment and think to yourself, where might some of that kinetic energy have gone? Please do that now. Okay, and you're back, and can you think of where the kinetic energy went to, since we seem to have lost some? Well, first of all, in a football collision, there's a lot of noise. There will definitely be a lot of noise created in that crash, and therefore some of that sound energy has to come from somewhere. It's going to come at the expense of kinetic energy. What else did you write down when you paused the video? Did you note that the two players, their shirts will rub together, for example? One guy's arms as he tries to tackle the other one, there's going to be friction there. And therefore, that energy has to come from somewhere. It's coming from the original kinetic energy. What else? It's entirely possible that one of the players gets injured. Maybe a bone breaks. Maybe he breaks an arm or a leg. Breaking something requires energy, and it permanently deforms the object. That requires energy, breaking of bonds, which cannot be recovered afterwards. People are not very springy, so when you deform them, they don't tend to spring back very quickly to the original, what's the word I'm looking for? They don't tend to go back to their original condition, that's what I was trying to say, and therefore that means the energy gets used for more permanent kinds of deformation. You may be able to identify other kinds, or other places where the energy went, but this is the basic idea. Now, as I'm talking about kinetic energy, I'm afraid you might start to forget about our good friend momentum. How does momentum factor into this? Is momentum still conserved, and if so, when is it? The idea that the law of conservation of momentum, LOCOM as I like to write it, is conserved, so P total is equal to P prime total. That is still correct if the net external force is 0. Now, on a football field, is the net external force 0? Let's think for a moment. The normal force is pushing up from the field, and gravity, of course, is pushing down. Now, at this point, you may argue, well, one guy is pushing this way. You could also argue that another guy is pushing that way. Friction, of course, would be acting, and this is an external force. However, we're kind of answering this question in what's called an ideal situation. And so, in the spirit of the question, we assumed, when we solved this the first time in the textbook there, that the net external forces were 0, so we were kind of ignoring friction. And therefore, in this question, yeah, we're going to kind of pretend that momentum is conserved. But in general, in any other kind of question, is momentum conserved? Yes, if the net external force is 0. Is kinetic energy conserved? If the total amount of kinetic energy before the collision is equal to the total amount after. And that will happen when things don't break, and when there isn't a lot of noise, and when bones don't break, and when things spring back to their original condition without being permanently deformed. It's a little tricky, so let's examine a little bit further. Here are some examples of what can happen to kinetic energy during a collision. One that you're very familiar with, maybe you realized it when you were doing the lab using the air track and the gliders, maybe you didn't, I don't know. But during a collision like this, where you see the bumpers in here are quite springy, let me zoom in here so that we can see. You know those springy little bumpers that you see there? If that's what we're dealing with, then let's think about what bumpers really are. They are pieces of metal that never break, at least on the air track they don't. They therefore never get permanently deformed, and they don't take up energy that they don't give back. They spring back to their original condition, and therefore they return the energy that they absorbed during the collision process. And there's not a lot of noise or friction during this kind of collision. Therefore, when the springy bumpers are involved in the collision, the kinetic energy tends to remain constant. We have an elastic collision. If we were to write the kinetic energy of the first object and the kinetic energy of the second object, we would find that this is equal to the kinetic energy of the first object prime and the kinetic energy of the second object prime. How do we calculate these? Easy. They are 1/2 mv squared calculations, just like before. This would be 1/2 m1 v1 prime squared, and this will be 1/2 m2 v2 prime squared. At the time that I'm making this video, this is semester 1 of 2013, the class has actually just completed an air track lab on momentum, and in class we're going to ask you tomorrow to calculate the kinetic energies of the objects involved. So if you're sitting at home and you have a little bit of spare time, you may wish to do that. Take out one of the trial runs for your lab and see, was the collision elastic or not? Of course, you may also ask the question, was there a lot of sound? Were any of the gliders permanently deformed? Things like that. Let's take a look at another example where kinetic energy decreases. This picture depicts a car accident. Now, let's think about what might happen in this car accident. It looks like it's a pretty head-on collision. So you might have M1, mass number 1, moving like this, and you might have it collide with mass number 2 looking like that. This might be your before picture. What would your after picture look like? Well, after this kind of collision, I'm trying to picture this in my mind. It looks very likely that M1 is going to be a big mess and M2 is going to be an equally big mess. And I'm guessing that it's possible that the final velocity of these two now joined objects could be 0. So I'll put a question mark here because it's not guaranteed, but it seems to agree with my experiences in car crashes, having seen a few myself. Here's V1. the initial velocity of object 1, and there's v2, the initial velocity of object 2. Now, question, and I'll ask you to pause the video as you answer this. How do the momentum values of the cars compare before and after the collision? And how do the kinetic energy values compare? Pause the video and think about those. Just answer them in qualitative ways, using words like greater than, equal than, less than. Go do that now. Okay, and you're back. Now, you should have noticed that the initial momentum of object 1, the first car, P1, has some value, and remember it's a vector quantity, so that's got a value and a direction to the right. But P2, the momentum of object 2, which has some value, will have some value to the left. Now, since these are vectors, it's very possible that they could cancel out and maybe, not guaranteed, but maybe add to 0. They'll certainly subtract from one another. After the collision, if both objects actually do stop, then what we'll be dealing with is a P prime that is 0. So guess what? Momentum can be conserved in this car crash. However, would the kinetic energy be conserved? Let's look. Kinetic energy is a scalar quantity. Therefore, the directions that mattered so much when we talked about momentum now have no bearing. So, let's look. The kinetic energy in the beginning for object number 1, EK1, it'll be some positive value. Remember, it's a scalar and you square the speed anyway, so negatives don't matter. This will be some value. EK2 will also be some value, which is positive because you're squaring the speed. It's a scalar anyway. So you're going to add these two up, and you will get EK total is certainly not equal to 0. It will actually be greater than 0 for sure. But in this collision where I asked you to imagine that the final speed of both objects is 0, what is the kinetic energy? The EK total prime, that would be 0. So look at this. We got greater than 0 for the initial kinetic energy, equal to 0 for the final kinetic energy. This is an example where EK is not conserved. Therefore, it's possible to conserve momentum like I showed you here without conserving EK. You have to look at each situation based on its own merits. Here's a very special case of a collision. It's called a completely inelastic collision, and as the picture with the figure skaters suggests, when you're figure skating in pairs like this, quite often the two skaters will come together. They will have an initial velocity, each of them, and the man will pick up the woman, and therefore they now move together with a common velocity and a common mass. Kind of like in this question with the football players. Now, as we saw with the football players, the kinetic energy declined quite a bit. In fact, it declined well over 90%. Well, this is what we call a completely inelastic collision. It's a collision where the masses join. And it is actually true that just like in the football example where the kinetic energy declined, in a completely inelastic collision, the kinetic energy always declines. You get the maximum decrease in kinetic energy. So you might want to commit that to memory, that in a completely inelastic collision, masses joining, you have a very large decrease in kinetic energy. And finally, let's look at an example where the kinetic energy actually increases. You know, we've been talking about kinetic energy either being the same or going down, which sounds kind of like a bad deal for kinetic energy. Can it ever increase? Well, here's an example where it can. An explosion. In this situation, I'm going to imagine that in the beginning there was a bomb that was fizzling like this, and it was, or not fizzling, just kind of getting ready to go off. In the beginning, how much EK was there? Well, actually none. The bomb was just sitting there. So EK total, all the particles that make up this bomb, in the beginning, 0. And by the way, momentum, 0, because if you're not moving, you can't have any momentum. So let's write that in. However, after the bomb explodes and you deal with this, what have we got? Well, we definitely have EK. It doesn't matter that the particles are going in different directions. Ek is not a vector quantity. It's a scalar. It's always positive because you're always squaring the speed. And therefore, each of these little particles here that's flying off is carrying some of the kinetic energy. So we can definitely write that Ek total prime is greater than 0. And right away, we can see that the kinetic energy has increased. This is not an elastic collision. It is inelastic. However, what about the momentum? Well, momentum is a vector, and so look at this. Some of the objects are moving that way. Some of the objects are moving that way. Although this is a three-dimensional collision, if I could simplify it, I'm just going to have you think about the proposition that just as many objects are going to the right as are going to the left, as are coming toward you, as are going away from you. It's a fairly symmetric kind of situation. I'm going to propose that equal masses and with equal speeds, the particles are going every which way, and therefore if you add up the vector total, you can actually get P total prime equaling 0. And so what does this mean? Once again, momentum conserved. Why? Because the net external force on that bomb before it explodes is 0. However, the kinetic energy, not conserved. This time we gained some kinetic energy. Did we violate the law of conservation of energy? No, this is not what elastic collisions are all about. They're not about total energy, they're about kinetic energy only. In this case, where did the kinetic energy come from? If you guessed it's from the chemical potential energy stored in the bomb, then you are correct. In fact, that's what bombs are. They are basically chemicals that store a lot of potential energy, and if you can create a chemical reaction that will release that energy very rapidly, you have a very powerful explosive device. Okay, anyway, moving on. So now, here's where things get mathematically tricky. I know I've spent a lot of time talking about the qualitative aspects of these collisions, but now we have to use our knowledge to do a numerical calculation, and as I've just warned you, and I'll do it again, you have to be very careful. Here is why. Here's the problem. Two equal mass gliders approach each other on a level track. I see a question, I start drawing. Let's see, what do we got here? Before the collision. The gliders are approaching one another. So here is glider number 1, and there is glider number 2. I'll call this M1, I'll call this M2. And because they're coming toward one another, I'm going to do this. I'm going to write this in as a V1 and a V2. Okay. Before the collision, glider number 1 is moving to the right at 2 meters per second, so let's designate right as positive. This is 2 meters per second. Glider number 2 is moving to the left at 4 meters per second. Now they tell you that the collision is elastic, so this is important. Sometimes the question will tell you that the collision is elastic. In that case, great. You don't have to do any of the decision making yourself. What they ask for is to determine the final velocity of the gliders. And the piece of information that I realize I have left out here is the masses. You're going to need to know the masses. Actually, sorry, no, I didn't leave them out. It said equal mass gliders. Okay, I feel better now. Since they are the same mass, we can just call them M and M. There we go. That could be a little joke, M and M. All right, going back to the analysis of the problem, so let's see what's happening after the collision. Afterwards, do you know what direction these objects will move? You might guess that the faster moving object will completely plow through the slower moving object, and they will both be going this way. Maybe you're predicting that this one will turn around, but so will the other. Who knows? You really have to solve the problem to find out, so let me erase all that stuff, and let's write in what we do know. We do know that this is M, we do know that that is M. We know that V1 prime is really unknown, and V2 prime is really unknown. So what can we write here? First of all, they told us that the collision is elastic. And if the collision is elastic, then we can write that the total kinetic energy before the collision equals the total kinetic energy after. That looks like this. As I expand that, mv1 squared, a half mv2 squared is equal to a half mv1 prime squared. Be careful with your symbols here. There's a lot of ways to make a mistake if you're not careful here. The priming and the squaring. Okay? Now, let's just borrow this and move it. Let's just move it over here for a minute. I want to get it all on its own. And here's why. The halves appear everywhere, so they cancel. The masses are equal, so they cancel. And that leaves me with a nicer equation to look at. For example, v1 squared, well, that's just 2 squared. And here's 4 squared. And over here, I still don't know these values. So I got to leave them like that. 2 squared plus 4 squared is 20. So guess what? I have my first equation here, which is telling me that v1 prime squared plus v2 prime squared is equal to 20. The problem is, that's one equation, but there are 2 variables. So I'm going to call it equation number 1, but I'm stuck. I can't solve at this point. What else do I know? Well, if you look at what's going on, this is an air track that is level. Well, if you're on a level air track, right away that tells you a few things. It tells you that friction is 0 because we're on an air track. And if we're on a level air track, then the normal is equal to gravity, just going in opposite directions. In other words, what I'm trying to say is F net is 0 on the system. Therefore, I can use the law of conservation of momentum. There is my second equation. From the law of conservation of momentum, I can say that P total equals P prime total. And so, what I'm going to get from this is P1 plus P2 equals P1 prime plus P2 prime. mv1 plus mv2 equals mv1 prime plus mv2 prime. Again, the masses will cancel. What have we got for v1? I designated positive to the right, so that gives me 2 in there, plus v2, which is 4, but to the left, that's negative 4. And so here we go. 2 minus 4 is negative 2, so now I know that v1 prime plus v2 prime is equal to negative 2, and so now we have ourselves a little second equation here, which is going to help us solve this system. Call this equation number 2. And what do we do at this point? Well, do you know how to solve this? If you think back to, I'm guessing grade 10 math, you would have solved systems of equations. I don't know if you solved a linear combined with a quadratic like we have here. However, it shouldn't be too hard. I'm pretty sure that you can all do this. You've seen it somewhere. What do? We're going to take the easier equation and we're going to isolate one of the variables. Let's isolate v1. So v1 is going to be equal to negative 2 minus v2 prime. And then we're going to sub into equation number 1 over here. So what's that going to look like? Well, we're going to have v1 prime squared. We still got that. But now it says to take v2 prime and square it. Sorry, I just realized I did the wrong numbers here. Let me try that one more time. We isolated for v1 prime, so I did a lot of things wrong here. There we go. That should be prime. There we go. Now let's sub in. So v1 prime squared is going to be negative 2 minus v2 prime and we have to square all of that like this, plus v2 prime squared, and that's equal to 20. Now, I know you should know this, but everyone makes this mistake, so I'm just going to do it for you to avoid the mistake. This is a bracket squared. You have to expand that bracket. Minus 2 minus v2 prime times minus 2 minus v2 prime plus v2 prime squared equals 20. Now, how do you solve this? Well, what you have to do now is expand this bracket, this times that, this times that, this times that, and this times that. Don't forget to add this term, and now you've got yourself a quadratic to solve. Now, in the interest of saving time on this video, I'm going to let you do this. However, what I am going to tell you is that when you get to the end of this, you are going to have two possible solutions. Because most quadratics give you two possible solutions, right? So you're going to have v2 prime equals something or something else, right? Because of the plus or minus in the quadratic formula. So when you do this, I'll just tell you what these numbers are, because I've got this done in front of me. You're going to get a plus 2 or a minus 4. Now, which one do you choose? Let me give you an example of some bad thinking. Oh, this is negative, therefore I'm not choosing it. Why is this a bad way of thinking? Because a negative velocity actually means something. It refers to the direction. Don't reject one of these answers just because it's negative. Instead, judge each answer based on its merits. Let's look at the possibilities. The quadratic is telling you that either v2 prime is equal to positive 2. What does that mean? Positive is this way. So v2 prime, this one here, could be 2 meters per second that way. This means that this object actually bounced backward. And that's a possibility. Two objects could collide and one bounces backward. Sure, no problem. Let's look at the other option, which was this one here, negative 4. That would mean that v2 is pointing this way at 4 meters per second. Is that possible? Well, on closer inspection, we see that the original velocity of v2 was 4 to the left. So if you choose this answer, then you're telling me that two things collided and that one of them didn't even change its velocity. It kept on going as before. That makes very little sense in a physical way. This is why we reject negative 4, not because it's negative, but because the answer doesn't make any sense. We choose this one because it makes sense. And then we use this, we're going to sub this into here in order to get v1 prime. And that one should also make sense. When you put in the positive 2 for v2 prime, you should get an answer for v1 prime that also makes sense. And that answer, by the way, ends up being, just so you can check, 4 meters per second to the left. In other words, negative 4. Which, by the way, yep, I can believe that this object started moving to the right and then bounced back to the left. Sure, no problem. All right, try this one on your own. The quadratic part gets messy, so I want you to try it to make sure you're comfortable with it. And then you hopefully will be a pro with these kind of collisions. Anyway, we finish up with some brief applications that are interesting and worth looking at. One example, of course, is car crashes. As we've seen before, during a car crash, you are almost always dealing with inelastic collisions, quite possibly the joining of the cars, and therefore a completely inelastic collision. Lots of noise is produced, lots of heat due to friction is produced, lots of things permanently break, which requires energy to break them. All of this means there is less energy available for the kinetic energy, the motion of the objects after the crash. Therefore, car crashes tend to be inelastic. Another one, atoms and molecules, a great type of collision to look at, a lot of physics in there. When atoms collide, they often have elastic collisions, which is to say that the kinetic energy does not get transformed into any other form. But this is not always the case. Sometimes atoms can collide and one of the atoms can gain some of the other's kinetic energy, and what will happen is its electrons can move to a higher energy level. And if this is the case, as you know from chemistry class, the electrons will go back down to their ground state eventually, and they will emit a photon of light. So in some cases, radiation can be the result. When molecules collide, what can sometimes happen in a collision is part of the molecule breaks off, and therefore you end up with new molecules, or maybe just bits of molecules, like smallest bits, which could be atoms. So molecules sometimes have elastic collisions, sometimes inelastic collisions. Sometimes they start rotating or vibrating differently than before the collision, and therefore they don't break into pieces, but new amounts of energy are needed for these new vibrational or rotational modes, and that's where the energy can go. And finally, there's a little toy that every kid loves to play with, every adult loves to play with. It's called Newton's cradle. To show you what this is, let's go to a quick a website actually. This is a great website. It's a little higher level at times, but it's worth checking out. Hyperphysics is the name. And one of their clips looks like this. Do you remember these little toys? They are called Newton's cradle. If you pull one ball back, you get sort of a pendulum action with one ball coming out both sides, never more. If you pull two balls back, you get two balls going off either side, never more. And if you pull three, you get three going on either side. And if you pull four, you'll get four going on either side. What is the reason? Well, let's go back and see what they explain. First of all, can you see why momentum is conserved in this collision? I'll give you a hint. Think about the net force acting on these balls at the moment of collision. You'll see that the forces of gravity and the tension in the string are balanced, so momentum is conserved. The other thing about these balls that you may or may not know is they are very, very elastic in terms of their collisions. They never get permanently deformed. They make a bit of noise, but not too much. They never break. They spring back almost instantly to their original position, and they don't heat up very much. So there's all sorts of opportunity for the kinetic energy to be returned after a collision. So what they write is that a half mv squared before the collision equals a half mv squared after. And on the next screen here, they show you, for example, if you pull two balls off to one side so that 2mv has to equal 2mv, the only way this can happen is if the speeds stay the same on both sides, and the only way this can happen is if the same number of balls always come off both sides. So, whoops, there, I'm trying to pause this right where I want it. If you try two balls out and one ball in, here's what happens. Now you end up with a situation where the momentum, 2 times the mass but a half the speed, which is what would have to happen, does not conserve the kinetic energy. Now, I know I've kind of rushed through this, so you should definitely look at it again, but it is a neat video to explain why Newton's cradle has elastic collisions with momentum conserved, and that's why you get all that fun stuff going on in there. What's the fact of the video? Did I forget? Didn't forget this time. The fact of the video is actually the definition of elastic collisions. And I would like you to remember this for the fact of the video quiz. In an elastic collision, Ek total, the total kinetic energy of the objects in the beginning, is equal to Ek prime total, the total kinetic energy of the objects after the collision. This is the fact of the video for you to remember for tomorrow's quiz. Thanks for watching and have a great day. Bye now.